Welcome back to the another problem. In this problem, we are going to check whether a number is a prime number or not. First of all, what is a prime number? A number is a prime if it does not have any divisors apart from the number itself and 1. Okay. So, for example, if you see here, these are some of the prime numbers 2, 3, 5, 7, 11, 13, 17, 19, because apart from the number itself and number 1, they don't have any divisors at all. And one special prime number here is the 2 because it's the only even prime number. And please note that 1 is not a prime number. Okay, so prime number starts from 2. Okay, cool. So let's see some of the examples of what is the expectation and what is the output. So if we pass 13, then 13 is a prime number, so we say output as true. If it's 16, we know 16 is divisible by 2 and 4 as well as 8, so we say it is false. If it's 101, then it's a prime number, so we return true. Okay, so first let me give you a clue on how to solve it naively. You can try it in the coding exercise and then we will talk about the solution. Basically, you just need to loop from 2 till number, whatever the number minus 1, and then check whether it is divisible or not. Okay, so that's all I can give the clue. I hope you understood what you need to do because I think it should be straightforward. So let's see in the solution video. Thank you. Okay, welcome back to the naive solution. So let's start. So let me create a new file first. 07 prime.js. Let me create a function called isPrime and let us take the number as an argument. Now we will start the loop from 2, but 1 is also not a prime number, right? So we will have an explicit condition for 1. So if num is equal to 1, then we will just say return false. Now what we will do is we will start the loop from I is equal to 2 and it will run until I is less than num and then I plus plus. Now inside this loop, what we will do is we will just see whether the num is divisible by the iterator or I. If num percentage I is equal to 0, then we know the number is divisible, which means it's not a prime number. So we will just return false. That's all. For all other cases, if we are getting out of this loop, then we know we have a prime number. So we will just return true. Okay. So let's add some test cases. I'll just copy and paste. I don't want to waste your time as well. So yeah, so these are the test cases. If you see is prime of 1, is prime of 101, is prime of 2, is prime of 13 and is prime of 50. So to recap, we are running the loop from 2 till number minus 1, and whenever the number percentage I or whenever a number is divisible by this I, then we just return false. So ideally this should give us false, and I think 101 is a prime, 2 is a prime, 13 is a prime. So false, true, 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 false. Let's see. So node 07 prime.js. Yes, as expected, false, true, 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 false. Great. So we have the naive solution. In the next video, we will talk about the better approach. Okay, welcome back. This is going to be our first better approach. Yes, there is one more better approach than the current one. In any case, let's see. If you remember, the last solution, the time complexity is big O of n and the space complexity is big O of 1. But if you know, let's take the example of square root of 9. Okay, so if you want to just, let's assume we want to find the square root of 9. The possible values are from 1 to 9, right? But we can just like that make it easier by, for example, what is the square root of 9? We know 3. Okay, but the idea here is that numbers above 3 can't be a square root of 9, right? Because if they do something like example 3.1 square, it is going to be greater than 9. Okay, so the maximum it can go is 3. So we are going to make use of this similar idea. Okay, the thing is, if you see, divisors always appears in pairs. So if it's 30, right, it could be 1 comma 30, or that means 1 into 30, or 2 into 15, 3 into 10, or 5 into 6. Similarly, for 25, it's 1 into 25 and 5 into 5. So basically what this says is that if we take this x into y is equal to n, which means 2 into 15 is equal to 30, or 3 into 10 is equal to 30, correct? But here we are going to make use of this similar logic. So how we are going to make use is that let's assume that x is less than or equal to y. Okay, now we can say that x into x is going to be less than or equal to n, right? Less than or equal to n. If it is equal to y, then it will at most go till n, but for other cases it will be definitely less than n, which means we can say x is going to be less than square root of n. Okay, so now what I'm trying to say is that rather than looping from 2 to n minus 1 and checking for divisibility, it is enough mathematically to check for the looping, check for numbers 2 till square root of n. Okay, so rather than n minus 1, we are going to check till square root of n. By this way, what's happening is like we are getting the time complexity of big O of square root of n, which is far better than the big O of n, right? Because always n power 1 by 2 is less than n. And space complexity, why? This is time complexity. Space complexity is as usual big O of 1. Okay, so you got the idea. We just need to loop from 2 till square root of n. So take this idea and try to solve the coding exercise. Let's meet us again in the solution video. Thank you. Okay, let's get back to the solution. So let me create a new function. So function is prime2, and let's take the num as well, and as usual we will check for 1. So if num is equal to 1, then let's return false. If not, we will loop through. So I will just copy this. So we're just trying to loop, but where is the optimization? Here is where. So rather than I less than num, we will check I times I is less than or equal to num. So this is the optimization. So now we have big O of square root of n time complexity. You need not change anything. So let's try to see how this test cases work out. So we need to get false, true to true, false. So let me save this and try to run again. Yes, as expected, we are getting false, true, 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 false, right? So you see, that's one small change, and we have made from big O of n to big O of square root of n. Great. So see you in the next one. Welcome back, guys. So this is going to be the next better solution. So the idea here is that we are going to have the similar time complexity, but we are going to reduce the number of operations. How are we going to do that? Let me give you the clue. What we will do is like at first, okay, we know one is not a prime number. Okay, let's leave that. Now as a first step, for whatever the number we passed, we check whether the number is divisible by 2. Okay, so if we check from this list, if the number is divisible by 2, we can ignore a whole lot, nearly 50% numbers, right? Because 2 is almost divisible one character ahead. So one number ahead. So let's say we are checking for whether a number is divisible by 2. So we can get rid of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, let me change the color so that it is more clear. Yeah. Okay, so now let's assume after checking for divisibility by 2, we also check for divisibility by 3. So 3 will be gone, 6 is already gone, 9 is gone, 12 is already gone, 15 is gone, 18 is as well, and then 21, and it goes on. So now after doing this, if you just check, right, we have almost eliminated most of the things. So what we have now is 5, 7, 11, 13, 17, 19. Could you get any pattern out of this? So let me give you the pattern. What we are going to do now is, like, since we are checking initially for the divisibility by 2 and 3, and we will also check whether a number is given a 1, and then if it's 1, we will just return false. So this time we are going to loop from 5 till the, as usual, I into I less than or equal to n. But what is the catch here is that rather than incrementing the numbers by 1 this time, so after 5, what we will do is, like, we will increment it by 6, because when we increment it by 6, here we will get by 11. From 11, we again will increment by 6, which means we will get 17. But then you might ask, Harish, we are missing the number 7. We are not checking for that, and we are not looking for 13 as well as 19. But do you see a correlation between this 5 and 7, 11 and 13, 17 and 19? Yes. You see, if it is 2 steps ahead, right? So there is one place vacant behind and then the next place. So it is kind of like plus 2. So what we will do is, like, when we are checking inside this loop for 5, we will also check for plus 2 as well. Same thing here. So plus 2, which is 13. So from 17 plus 2, 19. Okay. So rest of the logic remains the same as what we did for square root efficient implementation. Okay. So to be said, this solution works nearly 3 times faster than the square root solution. Okay. So now I have given you the idea behind how to solve this. So try to solve in the coding exercise, and we will meet again in the solution video. Thank you. Okay, now let's see how the most efficient solution works. Let me create another function. So function is prime third time. Yeah. This is the last time, guys, don't worry. So now, as usual, we will check whether number is equal to 1. If that is the case, we will just return false. But additionally, now what we are going to do is, like, we are just going to check whether number is equal to 2 or whether number is equal to 3. If that is the case, then we will just return true, because these are prime numbers. But why do we need to check for this? The reason being that we are going to start the loop from 5. So let I is equal to 5. Hence we don't have the opportunity to check for 2 and 3. Hence we are checking explicitly. Now we will also do I times I is less than or equal to num. And here's the important condition. We will be doing I is equal to I plus 6. Okay. Now inside this, what we will do is, like, we will check if num percentage I is equal to 0, or if you remember the second position plus 2, here is where we are going to check num percentage I plus 2 is going to be equal to 0, then we know it's not a prime, so we will just return false. Okay, great. And one more thing, we also need to check whether if num percentage 2 is equal to 0 or num percentage 3 is equal to 0. If that is the case, we will just return false. This is also a check which we need to add explicitly, because here we are not going to check for 2 and 3. Okay. If you remember, we said we will be checking this explicitly. So that's the reason I'm adding this condition. Hence, since we are adding this condition, we also need to add this definitely, else we can't check for num is equal to 2 and 3. Great. So now for all other case, if you are here, we know we have a prime number. So we will just return true. Great. So now let's see how the test cases fan out. So prime 3, prime 3, prime 3, prime 3, prime 3. Let's try running this. Yes, as expected, we get false, true to true, false. So that's all, guys. I hope you understand. And this solution works nearly 3 times better, as I said. Okay, great. So see you in the next problem.